This video is perhaps the most practical and useful video that I've made to date. If you go back and look at old IB exam questions, you'll find that there's loads of questions that ask you for ratios. And oftentimes you don't even really need to understand the physics in order to do the question, as long as you understand ratios and proportionalities. And that's what I'm going to explain to you in this video.
So what I've done here is just taken a random assortment of pages from the IB data booklet. So we're just looking at a bunch of equations that we use in the course. And a couple things I'd like to point out. Most of the equations just have one term. So you probably learned about terms in math class. So for instance, this equation here, it's got two terms, and the terms get separated by a plus sign. But most of the equations just have one term, right? And so it's just stuff multiplying each other or dividing each other, or we might have a power. So that's really just another multiplication. So most of the formulas have a single term with, well, variables, constants, etc., with stuff, I'll say, that multiplies, divides, and or has powers. And in a sense, they all kind of behave in the same way. Let me introduce what I like to call ratio proportionality equations. So if we've got two quantities, two variables that are proportional to each other, we can write that y is proportional to x. And what that really means is that if I were to plot a graph of y versus x, I'd get a straight line through the origin. So, well, straight lines would have an equation y equals a constant, well, really the slope, times x. But another thing that's true when you've got these proportional relationships is that if I have 2 points, x1, say y1, and x2, y2, then y2 over y1 will be equal to x2 over x1. That's really what it means to be proportional, that those ratios are always going to be the same. And if y were proportional to x squared, we could very easily write a similar type of equation. And that would be that y2 over y1 would be equal to x2 over x1 all squared. That would have to be true. So perhaps we see an equation. Y is equal to 3 pi x squared over z cubed. Well, 3 pi is a constant, so we can write that y is proportional to x squared over z cubed. And once again, we can write one of these ratio proportionality equations. That is that y2 over y1 will be equal to x2 over x1 all squared divided by z2 over z1 all squared. And typically here, we would invert and multiply that divisor, so we would get x2 over x1 squared times z1 over z2, and that was cubed. So we'd have an equation here relating two different values of y to their corresponding values of x, and in this case, z. So when we denote these 1s and 2s, we're really saying when y equals y1, x is equal to x1, and z is equal to z1. And when y is equal to y2, x is equal to x2, and z is equal to z2, etc. So typically x1, y1, and z1 here would represent a state of the system. And x2, y2, z2 would represent another state of the system. So let's take a little closer look at that. Here's a typical question where a ratio proportionality equation makes the question really easy. Pause the video, read the question over, give it a try, and then come back and see how it's done with the ratio proportionality. So we're looking for this ratio of A at P compared to A at Q. We definitely want to see a relationship between acceleration and the radius here. So when we go to the data booklet, we get these equations here. And if you think about it for a little bit, the period here, it's got to be the same for both P and Q. It doesn't change. So that's going to be a better equation to use. That is A equals 4 pi squared R all over T squared is better to use. Otherwise, we have to take into account that they have different velocities. So if A is equal to 4 pi squared over T squared times R, and 4 pi squared over T squared is just a constant, that means that A is proportional to R, which implies that our ratio AP over AQ should be equal to RP all over RQ. And RP is half as much as RQ. So we're going to get an answer of 1/2 here. So no muss, no fuss, quick and easy if we use the ratio proportionality equation. Here's a second question asking how many times more luminous than the sun is a star that is twice as massive as the sun. So you probably haven't studied astrophysics yet. But if you go to the data booklet, you'll find that there is a relationship between luminosity and mass of a star. And they don't give you an equation, they just say that it's a proportional relationship between L, the luminosity, and mass to the power 3.5. So we can write a ratio proportionality equation. We can say that L of this star divided by L of the sun will be equal to the mass of the star divided by the mass of the sun raised to the 3.5. And we know that that mass ratio is 2. So we plug into our calculator 2 to the power 3.5 and we get 11.3, which is to say that the star is 11.3 times as luminous as the sun. Here's a question that gave students a lot of problems, but it shouldn't have been a problem if they knew about ratio proportionality equations. So pause the video, try the question, come back for the answer. So we realize this is an ideal gas law problem, and our ideal gas law equation is PV equals nRT. Now, we're dealing with masses here, and mass is not in that equation. But the number of moles has to be proportional to the mass. The more particles you have, the more mass you have. So we can write here that PV must be proportional to mass. Well, R is just a constant. Mass times temperature. So mass would be proportional, just bringing things to the other side of the equation, would be proportional to PV over T. So that means that mass of P divided by mass of Q must be equal to P at P, V at P over T at P, all divided by, well, I'm going to invert and multiply. So I'll get a TQ all over PQ, VQ. And then let's see what ratios we know. P is held at a temperature of 200 and Q is at 400. So we can write here that TQ over TP will be 400 over 200, or just 2. We also know that the volume of P is twice the volume of Q. So VP all over VQ would be 2 to 1. We also know that we have this open connection between P and Q, and that means they have to go to the same pressure, which means that the two pressures are constant, and they're going to cancel out. So we're going to get 800 divided by 200. We're going to get a ratio of 4, and the correct answer is C. Here's a type of question that was very poorly done on exams. And I'm not even going to teach you the physics here. I'm just going to give you the equation and tell you what the symbols mean. R here is, of course, the radius of a nucleus. R0 is called the Fermi constant, but for us, we just need to know that it's a constant. It doesn't change. And then A here is the mass number. So if R is equal to R0, A to the 1/3, write a proportionality equation and solve the problem. Pause the video, try it, come back for the answer. Okay, so what we can say here is that R is proportional to, and we can eliminate R0 because that's a constant, it's proportional to A to the 1/3 power, which means that R of B all over R of A must be equal to A of B all over A of A to the 1/3 power. A of B, the mass number of B is 99. Mass number of A is 32. Raise that to the 1/3. And RB is what we're solving for. RA is equal to 7.0 times 10 to the minus 15. So we can solve, and we should get that RB is about 1.0 times 10 to the minus 14 meters. So easy problem to do if you understand ratio proportionality equations. You don't even need to know the physics. Here's a question from astrophysics, but you really don't need a background in astrophysics to do this question. You really just need to understand ratios and proportions. So what we're asked for is the density of star X. Density of star X divided by the density of star Y. And of course, density is just mass over volume. So this would be the mass of star X over the volume of star X, all divided by the mass of star Y, divided by the volume of star Y. Now, to divide fractions, we invert and multiply. So we're going to get mx over vx times vy over my. And we'd probably rate that in terms of the mass ratios and the volume ratios, as in mx over my times by all over vx. And now when we look at our graph, we look to see if we can get a mass ratio or a volume ratio, and we can't directly. We do get ratios for radius and for luminosity. This L here stands for luminosity. So what we really need is relationships between luminosity and mass and radius and volume. That is, the volume of a star, if it's spherical, and it will be 4/3 pi r cubed. 4/3 pi, that's just a constant, so that means that volume is proportional to r cubed. And that means that the volume of y divided by the volume of x has to equal the radius of y over the radius of x all cubed. And the radius of star Y is 0.1 r. The radius of star X is 10 r. So this is going to equal 0.1 r divided by 10 r all cubed. And that will come out to be 10 to the minus 6. The other important relationship we're given is this proportionality relationship between the luminosity and the mass. So luminosity is proportional to mass to the power 3.5. So we would like to get this ratio mass of x to mass of y, mx over my, that raised to the 3.5 should be equal to Lx all over Ly. And what I can do here is raise both sides to the 1 over 3.5, because that's going to isolate that ratio mx over my, because these two multiply together to give 1, and that's going to be equal to Lx all over Ly all to the 1 over 3.5. So my mx over my will be equal to Lx. Lx is 10 to the 4th over Ly, which is 10 to the minus 3, all raised to the 1 over 3.5. And if you plug that into your calculator, you get an answer there of 100. So now I can come back to this expression and say that px over py will be equal to mx over my, which is 100, times vy over vx, and that's equal to 10 to the minus 6. So I end up with a ratio for the densities of 10 to the minus 4. So let's try to summarize this process by writing an algorithm for using these ratio proportionality equations. So the first step in the algorithm would be to find a formula that relates the variables given in the problem. So let's suppose it was the ideal gas law. So our equation was PV equals nRT. So we've identified our equation. Then what we need to do is, if needed, rearrange that equation for the variable in the ratio asked for in the problem. So maybe they were asking for the ratio of the volumes for two different situations. So then you could write that V is equal to nRT all over pressure. Third step would be to eliminate all constants and rate of proportionality. So let's suppose it was given in the problem that the temperature was constant. R, of course, is a universal constant, so we would say that V is proportional to the number of moles divided by the pressure. Step 4 would be to write your ratio equation and solve. So that would mean that the volume in state 1 divided by the volume in state 2 would be equal to the number of moles in state 1 divided by the number of moles in state 2, all divided by the pressure in state 1 divided by the pressure in state 2. And of course, when we divide, we invert and multiply, so this would become N1 over N2 times P2 all over P1. So if you've been given those ratios in the problem, you're going to be able to solve for the volume ratio. So please take the time to become a subscriber, sign up for notifications, become a member, become a Patreon, make some comments, ask some questions. Any of your participation is greatly appreciated. Thank you.
And that's all for today, folks. Thank you very much.